Welcome. In this video, we are going to implement the great Proximal Policy Optimization paper, so the PPO algorithm from OpenAI. A very great algorithm, still state of the art today. We're going to implement it on the breakout game, even though our implementation does not depend on the environment. So these are the results we should get by the end of this video. So this is the agent playing the breakout game. And these are the average reward per episode on breakout. We see here we have many lines because we train many agents in parallel. And these are the average reward per agent. Okay, so very nice. So let's dive into the code. If you analyze this video a bit more, you'll see that the agent learns to dig tunnels through the bricks and then sends the ball in the tunnels. Maybe let's wait. Okay, basically, yeah, we see and then it destroys the game. Okay, so very cool. Let's dive into the implementation. We're going to use PyTorch as usual on this channel. We can start by implementing the actor critic. So basically that's a neural network with shared parameters between the actor and the critic. I will not explain in details or remind you what is the actor and the critic. In this video, we focus mainly on the implementation. If you're interested to learn more about reinforcement learning, PPO, DQN, DDQN, I have a full course about that on Udemy, and I will put the link in the description. Would you be interested? Okay, so we create the head of the neural network, so the shared parameters between the actor and the critic, and then we implement the tail where the actor and the critic use the features from the head to either return the probability per action or the value function. Okay, now we can implement the forward function. So straightforward, we compute the hidden features, and then we smear that through the actor onto the critic. Now we can implement a class, a wrapper on top of OpenAI environments, so that we can so that we can run many environments in parallel. There are wrappers that already do that. We could use them, but here I prefer to do it from scratch, so that we do everything from scratch, and our code is self-contained. We're using also this class from a stable baseline tree, but that means that if we were implementing that from scratch ourselves, and that's not very complex, everything would be self-contained. Okay, so basically class environments, that's just some basic Python programming. We're just having, instead of having a single environment with 8 environments or number actor environments within it, and we can interact with each environment one by one. So basically for each environment, we track the observations, we track if that's terminal state or no, we track the total number of rewards for logging, and that will make our lives easier when we implement the algorithm. We can implement the length, so how many actors we have in the environment, how many environments we have, so we can just return self.number actor. And then we can have a function to reset a given environment, so with a given ID. So basically we are resetting the reward for the current episode because we're starting a new episode, and we reset the environment at that index. Okay, and basically with breakout or with a few Atari games, what we do when we die, they explain that in the initial paper, the paper playing Atari with deep reinforcement learning. They explain that they found it beneficial to do a few no-ops at the beginning of the episode. It yields better results. So this is what we do. Every time we reset the environment, we do a few no operation. Okay, we can create a function to do one step in the environment. So basically that's straightforward. We do a step given the action that you take as input for the environment ID that we receive. We check if we lost a life or no. If yes, we say that's a terminal state, and then we can log a few values. Okay, great. One last thing, we can implement this get environment function. I'm not sure where it is. Okay, here, self.get environment to get an environment. So as the get environment will return a gem environment. So here the breakout environment. While using the processing from the paper, so we resize the images to 84 by 84 pixels. We put them in grayscale. So we go from RGB to grayscale, and we use a frame stack. So basically to stack the frame at time step t on the ones at time step t-1, t-2, t-3. That allows us to see the movement. If we have a single frame, let's say that we have the agent on the ball, we don't know in which direction the agent is going, nor in which direction the ball is going. But if I'm using 4 frames, I really see the movement. So it's a bit like a video, and we have more information to make our decision. We're also using max on skip environment. This is also explained in the paper. We skip some frames, and we take the maximum out of every 4 frames. Okay, great. So now we can implement the interesting part, the PPO algorithm. So we receive as input our environments. So the environments class, so that's a single object, but that represents many environments. T, it's equal to 128. So what is T? So basically, as always, I try to implement, just to start from the pseudocode and implement it in a straightforward way. So basically, T is the number of time steps that we run the environment, that we run the agent in the environment for. So we run them for 128 time steps, and then we only there we compute the advantage and then minimize the loss for a few number of epochs. So okay, so basically T case the number of epoch, 3, the batch size. So there is a table at the end of the paper with all those hyperparameters for the Atari games, including breakout, gamma 0.99, the device we're going to train on GPU, the generalized advantage estimator parameter. So basically that's something we did not have for DQN, but that is introduced for PPO, for example. The coefficient for the value function loss, the coefficient for the entropy regularization, on the total number of iterations. Here we train for 40k iterations. Okay, so we can start by creating an optimizer. So we take as input the actor critic that we'll create in our main loop, and then we can add the scheduler on top of that. Okay, we create some variables just for logging the reward per episode, and so that we can plot it, as you've seen on that page. The link for this code will be in the description if you want to have a look at the code. But yeah, basically we are going to log that, so we need to add some variables for logging. Okay, and now we can start. So basically we iterate over a given number of iterations. Okay. So if we have a look at this pseudocode, so basically that's the first line. We just iterate for a given number of iterations. I'm creating a few buffers, so to store what's happening when I'm running the agent in the environment. We're going to come to that later, but yeah, we're logging a few values. Then we iterate over each environment. Again, that's a straightforward implementation of the pseudocode. So we iterate over each actor. And then we run the policy in the environment for T time steps. So first thing to do, we iterate over each environment, and then we iterate for T time steps. Here, for keeping the code simple and concise, I'm doing a for loop, so for each environment, but we could do that in parallel, and things will be much more efficient. For example, if we have 8 agents, we should get almost an 8 times speed up in our algorithm. Okay. So basically for this environment and for this current time step, so we get the observation, so we get the current state of the environment. Here the state is just the RGB data, so basically what us human will see given all those processing. So by the end this is a 4-channel grayscale, but basically my point is we're not using the eternal state of the game. We're only using the information that humans have access to when they play the game. So then we feed this observation to the actual critic neural network to get the logits on the value. So the value again is the value function estimated by the critic. On the logits are just the raw logits from the actor for each action. Okay. Here we are not using, for example, a softmax to get probabilities or using a log softmax to get log probabilities. Why? Because at some point in my code I will need the probabilities, so P of X. But later in the code, I will also need the log probabilities. So I will also need log P of X. So for example, if I use a softmax to get the log probabilities instead of the logits, and later I want the log probabilities, so I take the log of it, I might have issues with numerical instabilities. For example, when you use the log softmax in PyTorch, it's much more efficient to use the log softmax than just the softmax and then apply the log on top of it. Because the log softmax will use a lot of tricks, such as, for example, the log sumexp trick, very important in machine learning. If you don't know about it, I invite you to learn a bit about it, just read a bit about it. But okay, anyway, basically we are using the logits directly, so that it will prevent us to have numerical instabilities. we're going to feed those logits to this torch class, so distributions.categorical. On this, we will be able to fetch the probabilities from that, the log probabilities as well. So this class will handle the numerical instabilities for us. So when we get the probabilities, it will compute it in a numerical stable way from the logits. And when we need the log probabilities, it will also compute them efficiently from the logits. But it will not just compute the probabilities and then take the log of that. It will directly compute the log probabilities in a more efficient way. Okay, so that's why we do that, and that's why we need this class. Basically, we could implement it ourselves as well, but this is to abstract that and to make the code simpler. Okay, if the environment is done, we just fire to reset the environment. Maybe that's not really needed because here we're already doing firing to reset the environment. So basically for Atari games, for some of them, when you lose a life, to be able to play a game, you need to fire, basically to tell to the environment, okay, we're starting again the game. Otherwise it's if it was in break, let's say. So basically we need to fire to reset the environment. Here that's maybe not needed because we already do it by default when we reset the environment. Okay, so anyway, on otherwise what we do if it's not done, we do m.sample. So the difference between DQN is that now our algorithm represents we learn a distribution over the possible actions, and therefore what we do, we sample from that distribution. Okay, we are not choosing action in a deterministic way. We sample from M. So given those logits, given the probabilities assigned to each action, we sample from that. Okay, then you can compute the log prob. So basically that's what I was saying. We need the log probabilities. So yeah, basically I'm computing the log probabilities using m.log prob, and I don't need to worry about the logarithm on instabilities that will be handled for me. Then we do one step in the environment. So for the given environment ID, we do one step in that environment, and we say reward equal np.sang reward. So we clip the reward for that's recommended in this paper, on the initial DQN paper, for better stability. Okay, and then we can log everything in our buffer. So for example, the observation, the action that we took, the log probability for that action, the value function, the reward that we got, on if this is a terminal state or no. Okay, if we are dead, so basically here we are just some kind of checkpointing on logging. So basically if the current current reward, so total reward for that episode, is better than the previous best reward, we just save the model. Okay, so that later we can make a video, is the one I shared at the beginning of this video. Okay, and then just logging the total rewards so that we can make the plot, and then resetting this environment with that environment ID. Okay, so basically to compute the advantage, so basically if we go to the paper, again I'm not diving into the maths, I do that in my course, so here we really focus on the implementation, but if you are lost with the maths, have a deep look at the paper, or do not hesitate to look at my course. Okay, so basically for computing the advantage at a given time step t, we need, it's a bit like a n step return. We need to have a look at the next time steps. So basically that means that, for example, when I'm computing, for example, AT is a function of delta t, and delta t is the reward, the direct reward plus the discounted, plus the value function at the next state, discounted, minus minus the value function at that state. So that means that when I'm computing the advantage at big T minus 1, I need the value function at big T. Okay. So in our case, we use big T equal to 128. So I need to compute the advantage going from 0 to 127. Okay. So from 0 to T minus 1. But when I'm computing advantage of T minus 1, I need the value function at big T. So that's why we do one extra step here. So just once we're done with that for loop for T time steps, we're doing an extra time step. We're computing the value function for the next state, st plus 1. So that later I can compute the advantage for T, for small t going from 0 to big T minus 1. Okay, So basically now that we've done that, we've computed this value, we can finally move on compute the advantage. Here basically that's a straightforward implementation of the of the equations from the paper. So basically we compute advantage on 80, we store that in this buffer that we created previously. So basically for a given agent with t advantage, so again going from 0 to t minus 1, and then with if we have eight agents in parallel, then we have if we have 8 environments, then we have 8. We need to compute that 8 times. Okay. So okay, we do that. We compute the advantage. A bit of logging. So basically, we could have done that later. We are going to use those advantage to train the neural network for a given number of epoch. But here, just some logging. So every 400 epoch, we plot the smoothed average reward per episode. This is what you see here. So we do that every 400 iterations. Okay, awesome. So now we can start training. So basically, because we train for many time steps, so basically if we have a look at the pseudocode, okay, basically what we do, now that we've accumulated data in our buffers, we've created the advantage. Now we want to train with for k epochs with a mini batch size m, smaller or equal to the total amount of data, which is n times t, so n the number of agents, t the number of time steps we used. So if I'm using 8 agents on 128 time steps, in total I collect, I believe that will be 1024 data points. Okay, so basically I'm creating a data loader, and then I can iterate over that data loader. So for epoch in range of k, I iterate for k epochs, and then we iterate over the data loader. And we get all those data points, so for example the advantage, so batch advantage, the current state, the action that was taken, the log probabilities, the old state values, okay? And all that will be useful to compute our loss. So the first thing to do is to compute, again, the logits and the value for the state, so for the batch state, oops. Yes, basically the actor critic is updated. In those 2 for loops, it will be updated. So every time we need to recompute those. A bit like when you do supervised learning, you compute your prediction, and then you compute the loss between your prediction and your target. And now the target is, this is why we computed the advantage, because the advantage will be useful in creating the target. Okay, so basically we compute the ratio between the new log probability and the old log probability, and we can also compute the returns, so basically the return at each time step. That is a function of the advantage. Okay. So basically the first thing to do is to compute the clipped store gate objective. So again, here that's just a straightforward implementation of the clipped objective from the paper. So basically we put that into code. We have many terms in the loss. So first there is the most important term. Well, they're all important, but the main loss function for this paper, like the clipped objective, okay? Then we had the value loss. So basically, basically the clipped objective is to train the actor, but we also need to train the critic. So to supervise him on the so we want to supervise it on the returns. So we take the difference between the value it predicts on the real returns, and we add the terms a regularization term for the entropy. Okay, so basically that's to favor exploration. Here we don't have epsilon greedy exploration approach. We just always sample from the policy. But to make sure that this is not a deterministic policy, that we allow some exploration, you add this entropy term. So now that we have the first part, the clipped store gate objective, we can implement the value loss. It's not explained properly in the PPO paper. There was this paper, you can have a look at it if you're interested, that study all the things that the authors do in the code, but that they do not explain in the paper. So there are a lot of small tricks that are done in the implementation, but that they do not explain in the paper, and they have a lot of impact in the results. So basically here, instead of just taking the value loss, so basically that's the value loss one, between the returns and the value, we apply also a clipped value loss. So basically in the same way that there is the clipped store gate objective, we do the same for the value loss. Okay, on that, again, that's not in the paper. They do that in the implementation. that's described in that paper, and that allows to get better results. So with our first term from the loss, clipped surrogate objective, with the second term, clipped value loss, now we can add the entropy. Well, basically we can put everything together. So here with the policy loss, here with the value loss, and here we are adding the entropy, and we can get it directly from M. So we can use this function m.entropy to get the entropy. Okay, on now that with the loss, we can do a standard backward pass. So we backward the loss, we compute the gradients, and then we do an optimizer step to update the parameters of our model. Something, again, that is not explained in the paper, but that they do in the implementation, that is critical, clipping the gradient or the gradient norm to make sure that things do not explode, and that's also explained in that paper. Okay, and also we created a scheduler so we can do one step of scheduling to decay the learning rate. So now that we've done all that, we can finally put everything together, and now that's very easy. We just set the number of vectors, for example 8 by default. We create 8 environments by using the class environment, and then we can call the, we create the model, the actor critic model, our neural network, and we feed that to the PPO training loop. Okay, I will hope this video was helpful too. I have a few more videos about deep reinforcement learning coming up. So yeah, if you're interested, subscribe, leave a thumbs up if you think this video was helpful, and thank you for your time.